Just throwing it in there.
Growth of 10 fingers in Laplacian and Poisson fields.
Thank you very much, Scott. And thank you, Bartek, and the other organisers of this workshop. It's great to be here. And of course, also many thanks to the organisers of the CAT overall program as well. So again, I'm going to play this trick of a couple of talks rammed into an hour. I think I can do it. So they are related, though. They are quite strongly related. So the first talk is I want to really invent a useful tool for studying what I call needle growth and finger growth, both of them characterized by being very thin in Laplacian fields. And then in the second problem I want to look at, I want to study finger growth and selection in a Poisson field. So the first part, I should thank Callum Miller, who helped me in the initial developments of some of that program. And overall, for both of these parts, I'd like to thank Dan Rothman at MIT Earth Sciences for his many discussions and also discussions with other members of his particular group. So let's start with a Cambridge photo. I think it's probably a Cambridge one. This is the Safman-Taylor experiments. Scott mentioned this the other day. It's in a Healy-Shaw cell. A Healy-Shaw cell is a couple of parallel plates separated by a very thin gap. In this particular experiment, you pump air into this one end, you extract fluid, that's this surrounding region here. It has a high viscosity, and very typically you get a single finger forming in this channel, and it's really a rather well-studied problem now, as Scott alluded to and Sally before in his master classes the previous week. One reason it's really well studied is it's really quite simple to formulate. You solve for Laplace's equation in the fluid region with a couple of very simple boundary conditions, namely that the pressure is constant on the interface and the normal velocity is the normal gradient of the pressure up to some sign there. So it's very simple to formulate, yet it has a very, even that simple problem is nonlinear, of course, because the interface is determining the unknown interface as part of the problem, gives rise to really quite remarkable dynamics in many situations. And that's really illustrated in this similar experiment where now you inject a less viscous fluid into a surrounding viscous fluid in a radial configuration, also in a Healy-Shaw cell, and you get this very typical fingering light pattern. There's interesting bifurcations going on, and so on. It really has a rich structure. It has a rich structure to look at, but also has a rich structure mathematically. And that's part of the attraction of these problems, is it's shown that these share a common mathematical structure with other branches of mathematics. Often very surprising connections can be made. And one reason for that is the underlying moment structure, integral structure of the dynamics. So spectacular, I think, is some of these patterns that this particular company will make lampshades, items of jewelry, and so on from Laplacian growth patterns. But often the instability gives rise to very thin fingers. So here's an experiment of a combustion front. So we have time evolving as we go upwards, and you get an instability formed on this smouldering front. By the way, this is also in a Healy-Shaw cell, so it's two-dimensional dynamics. And you get this perturbation which grows into these very typical fingering-like patterns. But you'll notice that some of the fingers grow very long, where some of the other fingers in between are arrested in their growth. They stop growing. And that's something I want to talk about as we go through this. This is perhaps not so easy to see, but this is beach reels. Those are familiar with sandy beaches, and Scott alluded to my background. I am. I'm lucky enough. When a wave runs up onto the beach and then recedes, water penetrates into the sand, and very typically when it does that, there's these erosion rills that form in the beach, and you can think of these as also being a Laplacian growth type phenomenon. In fact, the problem I really want to talk about is strongly related to this phenomenon. I just sort of throw this in because it's one of my favorite things on YouTube. This is probably not Laplacian or Poisson growth because there's other dynamics, other physics going on. This is a ferromagnetic fluid. I think the magnetic field is axial. I'm not quite sure about that. But in addition, this is in a Healy shore that's rotating. This, on the left series of panels here, this shows a particular snapshots in time of the evolving blob of fluid. And this, you can see it, if you watch this video, the circular blob sort of vacillates and then all of a sudden breaks into this finger-like instability, and then these start to roll up in very curious sorts of patterns. These are just amazing, some of these. It's spontaneous, yeah, it's instability, it just goes. It's great to watch. But that's a bit beyond the analysis that I'm going to talk about. This really motivates a lot of what I want to talk about. This is a particular region in Bristol, Florida, which is being well studied by the Rothman group at MIT Earth Sciences. And here's an overall picture of the valley network. So these are effectively depth contours. This gives you an idea of the horizontal scale. But there's a lot of interesting branching patterns going on and so on. And it's really one thing I want to talk about today is some of the characteristics of these branching patterns. But there are other really interesting things going on here, which I won't talk about today. If you focus on an individual valley or ditch, let's stick to valley today. If you focus on a particular valley, then you can ask the question, what's the shape of that valley? And that's an interesting complex analysis free boundary problem. But today I really want to focus on this branching pattern. So that particular region of Florida is characterized by a very sandy soil. Any rainfall that occurs is really sucked almost immediately into the subsoil, and it then becomes a flow and porous media problem, and we can talk about then the elevation of the porous layer above an impermeable layer, and the groundwater flux is given by this particular relationship here. It's Darcy's law, and P is the precipitation, so the conservation of mass is given by that. Putting all that together, you get Poisson's equation for h squared. The previous pictures I showed of Healy shore cells and so on are interesting. You can set them up in the lab pretty easily, but nature has also got its own Healy shore cells, and this is one of them. There's a lot of thin layers in nature, which means complex analysis is useful. This is one. The oceans and atmospheres are thin layers, and complex analysis of ocean vortices, for example, is a very good way to understand their dynamics. So nature's been kind, and in fact, this is a great place to, it's probably the best laboratory for applied complex analysis in the world. So how the network grows is a 2D interface problem in a Poisson field, or if we're prepared to at least neglect the effect of precipitation near the streams itself, we can take to a pretty good approximation. We can consider that the field evolves in a harmonic field. The network evolves in a harmonic field. So this area has been discussed in a series of papers, and this is just one example of those. So one remarkable characteristic of this Florida network is if you go out and measure, and they took almost 5,000 measurements of branching, there's a really strong peak for the branching angle of two streams being around about 2 pi over 5, 72 degrees. And that's something I want to come back to time again. And there's good complex analysis reasons why that angle occurs. But it's not only in drainage networks, but also in distributary networks. So it turns out that if you look at bifurcations in river deltas, and here's some examples of river deltas, then you also get this very typical branching angle which falls around 72 degrees again, and also in laboratory experiments you also see this. So for example, if you go and measure these angles and look at the apply statistics on them, it's around about this particular angle. So a recent paper I found in Journal of Geophysical Research models these distributary networks and river deltas, and these applied for various parameter regimes. Their ambition is to model Wax Lake Delta in Louisiana. I don't know if anyone here is familiar with that particular delta. Anybody? Yuri? You? Oh, great, yeah. Okay, so it turns out that this particular image here is using parameter values which are most appropriate to this particular delta. So again, you find these very thin branches, needle-like branches, which bifurcate at particular angles. So what I want to do here is really come up with a tool to try and understand and explore some of these branching characteristics. What happens to the branches after they bifurcate?
What's the difference between them?
So what they're doing here, they've got this particular model is shallow water flow over a porous bed, and it's friction dominated, so effectively it's Darcy's law, and that's coupled with a erosion model, which I don't quite fully understand yet, but when the fluid velocity reaches a certain threshold, it gouges, it starts to erode the bed. And these spikes or needles here are needles of greater depth. They're the channels within the delta. And so each of these will, for example, have different parameter values associated with the erosive model. I'm not fully up to details with that particular paper yet. That's one of my plans. One thing I should mention is that this characteristic angle of 72 degrees, I've already hinted that you can explain this rather well using complex analysis, and it's dependent on the fact that you have porous media flow. That in other words, the valleys are formed by groundwater erosive processes. So that leads to the idea that you can actually determine whether river valley networks are either driven or formed by surface flow or subsurface flow. And there's been a debate raging about Martian valleys, about whether they're caused or were caused, there's no water around it, well, we don't think there's certainly no surface water. Were these valleys formed by surface flow or subsurface flow? Turns out that these have a relatively narrow branching angle. So the latest is that, in fact, the branching geometry here, and that the Martian river valleys are probably most likely caused by surface flow and not a subsurface phenomenon. Okay, so here's really what I would like to talk about. So talking about Laplacian growth now. So we're in a harmonic field. We want to solve Laplace's equation in the upper half plane, and there are some slits in that upper half plane. These are our thin fingers. They're going to be slits. They can either be straight, and we're going to call those needles, or they can be curved fingers. I won't consider needles and fingers together. It's either or. If we can find a map from this upper half slit plane to a plane which to the entire upper half plane, then the solution now is immediate, because the solution here, by the way, the far field condition and the condition on the real axis, phi equals 0 on the real axis, phi tends to y at infinity, and that provides the flux for these fingers to grow. If you're familiar with diffusion limited aggregation, which is a process which is also closely related to this, this is equivalent or related to starting these particles off of infinity and marching them in a random walk and sticking them on a branch. So that's the role that boundary condition plays. Anyway, if we know the map, then we know the solution to this problem, because effectively phi is just constant going in the these are contours of the phi equals v, the imaginary bit of w, and if we map back, we get both the harmonic field and also the field of the harmonic conjugate about each of the needles and fingers. Of course, the difficult task is to work out that map. Yes, Nick.
What is the boundary condition on the needle?
Yeah, phi is 0 as well. Sorry, I should have mentioned that. Michael?
Yeah, I have a probably dumb question, but I missed how phi was related to the physical effect. What is phi?
Phi could be, say, pressure, something like that. Yeah, could be, or in the groundwater problem, h squared.
Oh, it was h squared.
Yeah, h squared. Yeah. So GT maps the slit z plane to the upper half of the WU plus IV plane, and we normalize that map, make it unique by insisting that it has this particular behavior as z tends to infinity, and I want to call the inverse map ft. I'm heading towards Loewner's equation, and it's typical to use g sub t for that particular map. So the sub t is not a derivative, it just indicates that g is a function of time. Oops. So what is the growth mechanism of these fingers and needles? So the price we pay for approximating a finger of actual thickness in shrinking it down to being a slit is that we have a velocity singularity at the tip. That's the price we pay, but we also gain things in making that approximation. What we gain is the dynamics becomes relatively simple. Yes, please. Yeah.
I think we don't fight on this, but what you want to do, because, well, the map is easy to find. So what next?
I would claim the map is not easy to find.
You have something else to do with this map.
Yeah. So I think that the crux of the problem is to find the map.
I don't follow.
So if we know the map,
No, but well, that's of course I understand.
In this case, it's restricted perhaps just to the tip.
No, but I just
it will be. It will be.
maps from the slit. No, this is easy. No, if we are talking just about G.
No, there's a dynamics associated.
No, so this is what I'm asking.
Yes. So the
Take the Neumann map of the boundary, and that provides the dynamics. How to
yes, and I'm just about to come on to how. So the price we pay is how to. So the price we pay is we've got a singularity at the tips of the needles and fingers, but the advantage is that if we know the velocity at the tips and needles, then we can somehow step forward in time. We can predict the motion of these needles and fingers with time. So all the motion is concentrated at the tip. And we also, by making this approximation, we avoid the problems of cusp formation in the Healy-Shor cells and so on. So what is the growth mechanism? So we have a velocity singularity at the typical inverse square root singularity. So let's integrate round a local radius at the tip. And if we do that, we get this particular velocity, and we're prepared to call that the velocity then, or approximate the velocity of our fingers and needles with this particular formula, which really results from integrating around the flux at the tip. And it's just the second derivative of the inverse map. So once we know the inverse map, we can step forward in time. We can compute, in principle, the motion of these needles and fingers for all time. For needles, yes. For fingers, no. And that's the difference. But more generally, the whole thing still works if you take some arbitrary power of this. So this is something I want to explore in the following 10, 20 minutes, whatever, is that, in fact, there's some arbitrary parameter, we'll call it a screening parameter, which also strongly influences the dynamics. Okay, well, there's a very classic tool for computing the time evolution of slits in the upper half plane, and that's Loewner's equation. And so for a single slit, and by the way, this has been around since the 1920s, it's a classic tool in univalence function theory, but it also becomes really rather useful here. So the time derivative of the map is given by some function d of t, which controls the growth of the finger, the speed at which it grows, and it has this form in the denominator. So what it effectively does, as time increases, the singularities build up in the real physical plane, and it maps them to the real axis in the mathematical plane. So as time evolves, the finger grows. And I'll give you an example, a very simple example to illustrate that shortly. So where a of t is the real driving function, so this is purely a real function. D of t is also real, and that's related to the growth speed of the fingers. And usually we solve this equation subject to the initial condition that g is equal to z. So we have the identity map. There's no fingers. They grow at t equals 0 from the real axis. And phi, our solution that we ultimately want, is just the imaginary part of this map. And we can generalize this in a straightforward way to n fingers. So this was the velocity. Recall that from previous overhead. And you can show that's related to these constants that occur in Loewner's equation via this particular expression. So if we know the velocity, we know this map, then we can use Loewner's equation to vect these fingers. Now, the case that's studied most in the literature is eta is -2, and the reason is that reduces these constants in Loewner's equation to being constants. There's no real reason why that should be the case, and that's something, again, I want to focus on. That, in fact, it's rather more natural to choose eta as 1, in which case these constants here are time varying. Now, of course, for one finger, it doesn't matter. You can scale time out of the problem. But for interacting fingers, 2, or fingers interacting with boundaries, it is important what d of k is. So that will become important, as we'll see. Just a further word on this, just going back, this Loewner's equation, some really interesting things happen when this is a Brownian motion, when this is a random function. You get the Schramm-Loewner evolution. That's a very well studied problem with applications in mathematical physics and statistical physics. But here the focus is on deterministic A. So a very simple example. Let's take a single finger. A of t is equal to 0. And so Loewner's equation becomes this. As I mentioned before, dot is a time derivative, so I can make this a constant just by rescaling time. And so without loss of generality, d to be 2. And solving Loewner's equation gives us this, of course. Applying the initial condition we get, which recall is that, the identity map at t equals 0, we can find out what c is. It's just that. And the tip of the curve, z equals gamma, satisfies g of t is equal to 0. The tip maps to the real axis. In this case, it maps to a of t, which we chose to be the origin. And so putting that particular expression into here, we arrive at gamma t is 2I root t. So it's just a vertical finger growing vertically in the pure imaginary direction, of course, with this particular dependence on velocity, on time. Other choices of A of t give more exotic curves, and as I've already mentioned, when A of t is a Brownian motion, you get extremely exotic curves, ones that have been very well studied from a statistical physics point of view. Just to convince you, you can get very exotic curves. These were done by an undergraduate student of mine, just playing around with solutions of Loewner's equation. With oscillatory forcing, these are some of the the curves that you can generate in time. So they're not necessarily just straight lines. Okay, but what about Laplacian growth? In Laplacian, how do we choose A of t? It is true that for any relatively smooth curve in the real plane, there is some A of t that will generate that curve. But really what we want to do is we want to decide what A of t should be in order to generate curves that solve the problems that we're after, Laplacian flows. And in particular, we want to look at geodesic growth. So how is A of t chosen in that case? So I just want to explain what I mean by geodesic growth. So find some chalk. So if we've got some finger now, I'm not talking about straight needles, but here's a finger. How do we know that at this particular point, we know it's going to grow with some velocity, but we don't know what direction it's going to grow. So what we do is we solve for the Laplacian field. In principle, we solve for the Laplacian field around that particular tip, and we grow the curve along the streamline, if you like, that grows, is tangential into that tip. So how do we do that practically? Well, we know there's some map, G of t, which takes the tip, here gamma, and maps it to A. So A is, and these conjugate dashed lines, the conjugate function to the pressure, if you like, are just vertical lines like that. So we grow it precisely in that direction there. So that's what geodesic growth means. We grow this particular finger in the direction of the streamline that enters the tip smoothly or tangentially with zero curvature. So that's geodesic growth, and that really goes back to Carlson and Makarov, and they showed that for the n-finger problem that the functions, the driving parameters of Loewner's equations satisfy this particular set of ordinary differential equations. So what Dan Rothman and his group have done have showed that this is equivalent to the principle of local symmetry. So that particular expression there, owing to Carlson and Makarov, is equivalent to this. It's also equivalent to the fact that you maximize the flux into this tip. They all mean the same thing. Okay, so that's the rule that we're going to use to grow fingers. So here's another example of an exact solution in the literature, which is a bit more interesting than the single finger growth. Let's take two fingers growing in the upper half plane. So here's two fingers, and they're going to grow at the same rate. How do they interact with each other? So again, without loss of generality, we assume that the situation remains symmetric for all time, so we can rescale time so their growth rates are constants. Let's choose them to be 1. And because of symmetry, the A1 is minus A2, let's call it A of t. We can solve for A of t exactly because it satisfies that equation, substitute it into Loewner's equation, and we get this particular solution. And by the same procedure as before, the tips satisfy this particular equation. And here's a sketch of that. Here they are. They grow away from each other. So they feel each other, and the net result of that interaction is for them to grow away. Now, what's really of interest here is that they grow away from each other and make an angle eventually with asymptotic angle of pi and 5 to each other. Now, recall, going back to that stream network problem, there's this interesting angle of 2 pi over 5, double this. Well, that's now pretty easy to see why it's 2 pi over 5, because in fact, what's happening in stream branching is you're bifurcating from a single branch, and then we get the 2 bifurcating secondary branches look like that, and that's easy to obtain from this really just by conformal mapping, squaring it up basically, and that's why it becomes 2 pi over 5. 2 pi over 5 is special. in other words, because that's the critical angle such that these local symmetry is such that the streamline entering the tips is precisely in the same direction of each of these. So that's why there's this interesting angle of 2 pi over phi. And that's strong evidence that Laplacian dynamics is at work in Florida. Okay, so now I want to talk about needle growth. Needle growth is special. It's in some sense it's easier because we know the direction. So once you have a straight needle, you've set the direction forever, and all you need to calculate the evolution of needles is their speed of the tips. So this is now much more straightforward to compute because it is just the Schwarz-Christoffel transform. So here you have something like this. You have a bunch of needles, straight needles, emanating from the real axis. This is a polygon, degenerate polygon. You can map that to the half plane, and the map looks something like this. There's always some choice to make in Schwarz-Christoffel transforms, and we need to choose A of t such that it satisfies that correct boundary condition at infinity. So A of t is the one that we choose to satisfy that, and then that sets these other coefficients. In principle, it's easy to write down, but what's really hard practically is to work out what these coefficients are. That's a difficult problem, a very difficult problem. But luckily, there's a very efficient and accurate way of doing that using Tobin-Driscoll's Schwarz-Christoffel toolbox for calculating these parameters of the Schwarz-Christoffel map. And once you have those parameters, advecting those needles is then a very straightforward process, and I'll show you some examples shortly. There's another way of doing this, and this is based on some work by Jonathan Tsai, a Cambridge PhD student, and the idea here is, in fact, there is a way of reducing those parameters to a set of ordinary differential equations which are relatively straightforward to solve, here, for example, as they are, and they will then, subject to correct initial conditions, give you the parameters of the Schwarz-Christoffel map at any time. Once you know those, you know the map, you can work out the velocity of the fingers. These? Not necessarily. Not necessarily. No. So the velocity of the finger, recall, the velocity of the finger is that. And that's potentially a function of time, and that's what makes it interesting. So here's a very simple example. Let's take two fingers which rise in tandem at the same speed and maintain symmetry, and you can show that you can use either of those two methods, and the solid line gives their height as a function of time. But also the form of the Schwarz-Christoffel transform makes it convenient to do asymptotics on these growth, and you can compare that. So the asymptotic results are the dashed lines, and they agree pretty well with the numerical results. And in fact, they do in the appropriate limits. When you break the symmetry, then things get more interesting. So here we're starting with two fingers with slightly different lengths. And they initially grow together, but as soon as, but the symmetry then really is broken with one, the slightly larger one growing much more rapidly than the other, and eventually the other one comes to a halt. And really, that's something we call screening. The longer fingers suck up more of the flux from infinity, and the smaller finger in the shadow zone of the larger finger really doesn't get fed. It stops growing. And that screening is also evident in this particular problem. So here we have, this is a snapshot of a pair of needles which have the same initial length, slightly different initial lengths, they're angled towards each other. And the one that's slightly longer eventually dominates. This one slows to a standstill, and this one carries on. So here's their heights as function of time. And this is the one that's obviously comes to a standstill. You can have a bunch of fingers. So here's 9 needles, all growing vertically. The symmetry is broken because, for example, the outer needles don't have neighbors on their right or left, depending on which one they are. And so there's different growth rates amongst the needles, and they maintain this symmetric pattern. And after a while, it's just these 2 outer needles that grow rapidly, and all the others between them stop for the same screening reasons as I mentioned before. You can play the same game in a channel. The beauty of this method, based on the Schwarz-Christoffel toolbox, is you're not necessarily restricted to the upper half plane. You can come up with other reasonably exotic geometries, channels, wedges, whatever you like. So here's 9 needles in a channel now. So here we have walls that satisfy phi x is equal to 0. And you can map. There's an extra step required here. But anyway, you can still do this problem. And the needle that survives the long one is now in the middle. Okay, so that's straight needles. They're relatively simple because all we needed to know is the speed of a needle. The direction is set by the initial needle direction. But what about curved fingers? Can we use the same sort of ideas to compute the evolution of curved fingers? Turns out we can, just by discretization. We can chop up a curved finger into straight line bits, and then once we have, say, a first couple of segments, that's again a polygon, we can map in the same way, and we can use this idea of local symmetry to find the direction and length of the next next segment. So applying that particular procedure, we can test it against the 2-finger problem for which we have an exact solution. So these different colors here represent different segments, different iterations in the process. And here's the comparison. There's the exact solution, and eventually we get convergence towards the exact solution as we chop it up into ever finer straight line segments. So it appears that this is a reasonably effective way for studying fingers. So let's do a problem which we can do only via this method. As far as I know, only via this method. We can't do it analytically. So suppose we have an initial bifurcation. So this dark line here is a semi-infinite needle. It's bifurcated into some angle. One part of it's still going straight on, and we've got a little side branch here in boldface. And we want to compute the evolution of that small perturbation. How do those 2 fingers evolve over time? And it turns out you can apply the method that I just talked about to compute the trajectories. In fact, you can do this analytically if the speeds are constant. That is, we choose our screening parameter eta, so the d's in Loewner's equation are constants. You just get this solution by conformal mapping. Conformal mapping you need to do numerically, though. But you can do it. And this compares the numerical solution with the exact solution. And also here, what I've done here is plotted the tangent angles between each of these branches, and you'll see that they eventually go to 2 pi over 5. So again, this is really something that these branches want to do in a Laplacian field. But for other values of eta, other values of screening parameter, we don't have the ability to map this exact solution. So we need to compute these numerically. So what I've done here, for different, this is a semi-infinite branch. Here's the initial bifurcation. How do these behave for different choices of our screening parameter? So for example, when eta is -2, that's when we have d equals constant in Loewner's equation. We get these solid curves. So this is the behavior of the 2 branches. But for these other choices of eta, we get different trajectories for each of these fingers. So these dashed lines corresponds to each equals 1. And for each equals 4, we see that this branch carries on quite merrily, but the other branch, you can't see it. It just stops. It stops moving. It's highly screened. The bigger the value of eta, the bigger the screening effect. And there is good evidence that this, for example, this that screening does occur in this Bristol, Florida region. So in other words, this convenient choice is not a good choice for that particular region. So this concludes part 1. So we can compute needle growth is usefully studied using the Schwarz-Christoffel map. You can do all sorts of things, asymptotics, numerical computation, using the SC Toolbox. And we can also reduce to a coupled system of ODEs for the SC parameters, and they all have nice agreement with each other. Strong screening effects when eta is 1. That's the natural choice of this screening parameter. Curved fingers can be discretized and their evolution computed using the Schwarz-Christoffel toolbox, coupled with this principle of local symmetry, which I talked about over there. It's easy to extend to other polygonal geometries. Other PDEs, well, I'm going to talk about other PDEs shortly. So, and there are other applications, river deltas. So, part 2. So here's some really interesting experiments, numerical experiments by Cohen and Rothman, which appeared a couple of years ago in Journal of Statistical Physics. So what they've done is the following. So in this particular left panel here, what they'll have done is start with a couple of fingers and grow them with time, and they're solving Laplace's equation, beg your pardon, Poisson's equation now, subject, so this is Poisson's equation, subject to phi equals 0 on boundaries and fingers with 0 flux at infinity. So the flux to this problem is the rainfall. Okay, the rainfall, that's this term here, it's the source term. And interestingly, they show that whatever initial starting choice of trajectories, you end up in one of these two branches being selected. They all follow eventually those paths. Just a curiosity I'm not going to talk about because I don't know anything about it, but the golden ratio came up a couple of times this morning. There's also here in this picture, turns out the ratio of this height here from the real axis to when it settles down to this straight path divided by that is the golden ratio. Remarkable. Okay, they also did it for, well, it's about the golden ratio. For 3 fingers, they also did the same set of experiments. Here, the central finger, not surprisingly, settles down to the center line, but the other 2 fingers will make well-defined distances from the channel side walls. So the ambition here is to try and understand how they get these results. Is there another way of predicting analytically these distances, LW, LC? So what we're going to do to model this, there's a typo here, that should be Laplacian of phi, not psi. So we're going to solve, this is our problem, I've turned it on its side. Poisson's equation in the interior in a channel of width 2, but ultimately width 1. I'm going to assume symmetry. And our task is to find that distance there. That's what we really want to do. So we're going to assume that these settle down. So a steadily propagating problem in the infinite strip, y between 0 and 1. And to proceed, let's take care of this -1 by adding in this particular term and solve this here, the harmonic problem for psi, and with these boundary conditions. The only thing that really changes is that psi is now some constant on this finger. And that needs to be determined as part of the solution. Well, we can solve this again. It's just Schwarz-Christoffel map. This is a slit channel, and we can map this to the half plane. Again, there's another map. We can take it to exploit the fact that this is a line of symmetry. You can bump that up to this imaginary axis, and we have a sequence of maps. and we can write down the potential in this plane here. So we can get at the behavior near the tip. That's necessary because we need to apply our principle of local symmetry. That's part of the solution. The parallel finger can't be at any old height above or distance from the channel wall. It's got to be at the precise height that local symmetry is satisfied at its tip. So how do we find that? Well, we just expand, we'll look at the behavior of the map near each of the tips, and I'll gloss over some of the algebra. It's possible to do. In the Laplacian case, it's very straightforward. In the Laplacian case, this term vanishes. In the Poisson equation case, it needs to be added to this term. This is the inhomogeneous term that we added to satisfy the forcing term of Poisson's equation, where VA is that. And so applying that to our particular expressions, we arrive at an algebraic expression for a parameter A. We can solve for that in the permitted interval that A is between -1 and +1, and we arrive at the distance, and that compares well to the numerical experiments of Cohen and Rothman. You can do the same thing for 3 fingers. It's a little bit more challenging because there's an extra parameter here. There's a finger growing along the center line. We make an assumption here that that finger distance from infinity is the same length as this finger here that exists to one side of the center line. So that's an assumption we make. So there's an extra parameter that comes with that, parameter B, but that's determined by that equal distance. And we get this particular equation for principle of local symmetry, and assuming the finger lengths are the same, we arrive at that relationship between A and B. And you can solve those numerically, and again, it agrees pretty well with the numerical experiments. But you can do this for n fingers. In principle, it's now straightforward by the same procedure. You now have n fingers, and if you assume they're all of the same length, again, that's perhaps a little bit an iffy assumption, because we saw in our needle growth problems they don't necessarily grow at the same rate. But assuming that does, and they do in the numerical experiments of Cohen and Rothman, because that's just the way they grew them. They assume that they grow at the same rate. So, for example, n equals 4, you can determine these distances from one of the side walls of each of the 2 fingers on that side of the center line. But you can compare that to Laplacian growth. Laplacian growth you can do exactly just by conformal mapping, and again that has a different distance from the center line. So there's an interesting question here. Poisson growth, you get a particular selected path. Laplacian growth, you get a different selected path. And I think that's interesting for the following possible reason. Can we use this to perhaps look at river systems and infer past climate? It seems that the forcing on the right-hand side, which is related to precipitation, determines which path you select. So is there a continuum between the two, which is you're able to then, if you like, do some sort of inverse problem and infer precipitation thousands of years ago, or changes in precipitation. It's an interesting idea. So let me just conclude then, part 2. So we've found an exact solution for steady thin Poisson fingers. And can we consider other geometries, boundary conditions? That would be an interesting thing to tackle. Can selected paths be used to infer forcing, just what I mentioned then? Can we infer the precipitation? Thank you. Nick?
The magic bifurcation angle of
Yep.
72 degrees?
Yep.
That was for Laplacian, right?
It is, yeah.
Is that altered by precipitation?
Probably not. And the reason is that locally, it's still, even in the more general Poisson problem, locally, near the branching event, it's still Laplacian once you get close enough to that bifurcation dynamics. It's though it's probably almost certainly the case that away from that bifurcation, and they'll start to interact through Poisson interaction, and it won't necessarily be 2 pi over 5. So it will deviate from 2 pi over 5. But locally, yes. Mm-hmm.
Quasi-conformal map techniques have ever been applied in this context for this kind of modeling?
So they didn't quite,
Quasi-conformal map.
not to my knowledge. Yeah.
And I was just wondering, is geodesic growth inherently smooth? That seems to be the...
It is, yes. Everything here is nice and smooth, and geodesic growth appears to be. I know no counterexamples, put it that way.
That's the kind of growth that is typically observed.
It is, yes. In these sorts of geophysical problems, yes. Yes. Yeah.
I have a few questions, but I'll just ask one. So, is there any validation studies? I have not kept up with the literature since the last 15 years or so, where someone does numerical work working in a Healy saw with some regularization and compares with this kind of approximation. I know it's a tall task because we can't go very far, but with modern computing abilities, let's hope we go farther than we can otherwise.
Yeah, I think we're getting away from the very thin fingers that we're talking about here. Are you talking more generally about Laplacian growth problems and numerical approaches?
So basically, does one see anything like this if you actually have put in some width and put in some representation or some other regularizations and study the long-term numerical, the long-term dynamics?
Yeah, not to my knowledge, no. Scott might know more though.
Finite with needles, then your model is ill posed, is that right?
Yes, so you might get things like cusps and so on.
You'll need to put something in.
Yeah, that's right. But that's the one advantage of doing this is one big advantage is that you avoid things like cusps and so on and finite time breakdown. All your misbehaved stuff is lumped into the tip, and the tip grows.
Another regularization that's relevant for this application with ground modifying.
Well, there's there's a bunch of other regularizations, kinetic undercooling and so on. But in this particular sort of model, I'm not aware of any. No.
Yeah, so in the case there are n-finger actual n-finger steady solution. I don't know if you're aware of it. But it suffers from selection problem.
Mm-hmm.
So I'm wondering, so this way of doing it is, of course, it's selecting at a certain width. It'd be nice to compare that.
Into finger width, yes.
There are n-fingers, you're aware of it. There are n-fingers.
Yeah.
With different widths that travel in the same rate.
Mm-hmm.
And that there are exact solutions like that. Or actual fingers.
There are, in a channel there are, sure. Yeah.
So, and this, the way you're doing it, is actually selecting this thing. So it'd be interesting to compare.
Yeah, I agree. Yeah. Mm-hmm.
Have you thought about putting tip splitting?
Yeah, tip splitting is really interesting. So the way we tackled it here is assume that it has split. But yeah, I think there'll be you need to come up with a criteria, and that's the key. That's the but it's interesting if you go to Loewner's equation, you have that forcing function a of t. If you make it jump, so if it's discontinuous, you get an interesting thing that happens. So you might happily be, if a is constant, then we know it grows vertically. But then if you shift a to all of a sudden it jumps, then you'll get a side branch growing. So that's like a splitting event. Unfortunately, if you pursue that, this is stopped. This stops growing. But you know, there might be other ways around it. But you know, this model, there are three things you need. You need the speed, you need the direction, and you need some criteria of splitting. And that's something I haven't looked at.
Yes, I was afraid to ask you, but I decided eventually to ask.
Please.
So apparently I don't quite understand the very beginning. So here is show problem, so it is a pose problem. And so the formation of fingers, it is kind of one of the manifestations of it. And I thought that the question is to try to describe formation of fingers. But what you're doing, you already somehow have them.
That's right. We make this. So the idea is we have fingers. Let's see how they behave, and we know there's some of the motivation is there. There's laboratory experiments. Fingers form, very thin fingers form. They grow. So that's what these ideas are looking at.
Related question, probably, then I see that it's okay. So I actually asked already that there is this series of papers about 10 years ago, which was originated with this Miniev-Einstein work, and then it was kind of taken over by Pavel Wigman and his group, and Makarov also was, I believe it is the same Makarov as you mentioned him, right? And also there was this, and I believe that they kind of found the relation of the problem with normal matrix models.
Yep.
And if I understand correctly, they try to describe the creation of fingers using some Pinlever-1 equation. So any comments?
Yeah, well, that particular enterprise has established some fascinating connections between this simple physical problem and random matrices, quadrature domains, so on. Yeah. And those fields have helped each other. I don't know if they've answered fundamental questions in this particular area.